Okay, the first couple of problems are actually using properties of logarithms to solve exponential equations. So I think I'm going to do, I think it's 1 through 9. I'm just going to do this on one video. And let's go ahead and put these pictures up here. Okay, so here we have e to the natural log of x is equal to 4. We're supposed to be solving for x to an accuracy of 3 decimal places, which means I need to get my calculator. But the first one I don't have to worry about too much because one of the properties of the exponential function is it is an inverse of the natural log function. So when we have e to the natural log of x equals 4, we can just replace the left-hand side with x equals 4. Now, if it had been e equals, let's say, 4 times the natural log of x, that does not equal 4x. That doesn't work. What you have to do is you'd have to move the coefficient that's in front of the natural log and make that the exponent. So it would be the e to the natural log of x to the 4th. And then that would be equal to x to the 4th. So you can't have anything in front of the natural log to be able to use that kind of property on the inverse function. Okay, just get my calculator. Okay, number 3 is e to the x equals 12. Okay, so we don't have it in this form, but we can take the natural log of both sides. Which what that does is it allows us to use the other property of inverse functions, which is the natural log of e to the x. So the other inverse function is the natural log of e to the x is equal to x. The first one we used, that e to the natural log of x is equal to x. So this is the properties of inverse functions, f of g of x, g of f of x equals x. So what we do is we take the natural log of both sides of the equation, and then we use inverse properties, or the other property that you can use is the fact that this is a natural log, so you can move this outside the integral like that. I mean outside of the natural log. And then the natural log of e, well, the natural log is the log to the base e, so when you have the same base as the number here, you just get 1. So you can do that in either case. You could have gone directly here to x, because this inverse properties of these two functions, or you could take this out and then take the natural log of e, and you find out that's equal to 1. So the final answer is the natural log of 12, which if you use your calculator, you get 2.4849, so we round down to okay, number 5. 9 minus 2e to the x is equal to 7. Again, we're solving for x, so we need to get, first thing we need to do is get e to the x by itself. So that means solving for e to the x. So the first thing we do is we subtract 9 from both sides. And that'll get rid of that, so you'll get negative 2e to the x is equal to, and you get negative 2, so we divide both sides by negative 2, and we get 1. E to the x is 1. So then we take the natural log of e to the x is equal to the natural log of 1. Well, the log of 1 is always 0, no matter what the base is. So base to the base e, it's 0. To base 10, it's 0, etc., etc. So now the left-hand side, because of this inverse property, just becomes x, and the natural log becomes 0. And you can go back, you think, that doesn't make sense. But if you go back here, e to the 0, if you put x equals 0 in here, e to the 0 is 1. So you get 1 times negative 2, which is negative 2. 9 minus 2 is 7. So it doesn't work out. Okay, number 7. 50 e to the minus x is equal to 30. Again, we're going to solve for e to the x, so we're going to divide both sides by 50. And 30 divided by 50 is the same as 3 divided by 5, which is 0.6. Now you might say, well, actually you can't do this. So we're going to take the natural log of both sides. So you get natural log of e to the minus x is equal to the natural log of 0.6. And you can do it here because there's no coefficient in front of the e. If there was, then you'd be in trouble. But because it's just e by itself, this works. I'll explain what I mean in just a second. So, and the natural log of 0.6 is going to be a negative number because the natural log of anything between 0 and 1 is negative. So we get negative 0.51. So we divide by -1 or multiply by -1, and we get x is equal to 0.51. Now let me just explain what I was talking about. If I had, if I took the natural log of 3 e to the x is equal to something, the natural log of 2, say, I can't bring the x out at that time. What I should have done is this original equation would have been 3e to the x is equal to 2, and I should have divided both sides by 3. So I would have got e to the x is equal to 2/3. Then I would have taken the natural log of both sides. And then I would have worked. But I can't have a coefficient in front of here, just like I can't have, well, that was problem or whatever it was. Okay, let's just check, see if it works. So if you take e, so do that on your calculator, e to the negative 0.51 power, because x is 0.51, so it's even negative 0.51 power. And I did something, I know I did. I have to put negative, not minus. And I get 0.600 times 50 is 30. So that does work. So check. So that's the thing about these problems. You can always plug the answer in and check to make sure you've done it right. Nobody really wants to spend that much time doing it, but sometimes it's worth it. Okay, number 9 is the natural log of x is equal to 2. So this is the other way around, where we use the other inverse property that says if we say e to the natural log of x equals x. So to get in that form, we have to basically take the left and right hand sides and make those the exponents. So we get natural log of x equals 2, so e to the natural log of x equals e to the 2 power. Then we can use the inverse properties between logarithms and exponential functions to make the left-hand side x and e. So if we take e and we square it, we get 7.39. So if that'll work out. If you take the natural log of 7.39, you get 2. So my checking was the natural log of 7.39. And plug it into the calculator to get 2, which is what we originally started with. Let me see if I got any more of those. I can't remember. Okay, that was all that I assigned. I'll just work a few more if you just need some more help. There's just a couple of examples, so if you understand it, you don't have to watch it if you're still needing a little more help with logarithms. So this is problem number 11. And so, again, it's just like this problem. So we're going to say we're going to make each side of the equality be the exponents, like that. And I've got to make sure I subtract 3, not 2. And again, there's nothing in here. There's no coefficient in front of the natural log, so we can directly say that the left-hand side is x minus 3, and the right-hand side, we already know from this previous problem, is 7.39. So you add 3 to both sides, and you get 10.39. And again, if we plug this in here, 10.3 minus 3, 10.39 minus 3, and then so it's just basically this problem, except I added 3 to it. let's look at 13. So we have the natural log of the square root of x plus 2 is equal to 1. Same deal. E to the natural log the square root of x plus 2 is equal to e to the 1. The right-hand side becomes just, well, actually there's two ways of doing this. I'm going to show you both ways. So let's say I didn't take the square root, but I just left it in there. So you would get the square root of x plus 2 is equal to e to the first power, which is 2.718. Just e. Square both sides, so you get x plus 2 is equal to 2.718 squared, be 7.39. And then you would subtract 2, so we would get 7.39 minus 2, 5.39. The other way of doing this would be you could use the property of the logarithms to take this expression, which we can write in exponential form this way. You take that outside, so you have 1/2 the natural log of x plus 2 is equal to 1. Multiply both sides by 2, so you get the natural log of x plus 2 is equal to 2. And then you do e to the natural log of x plus 2 is equal to e squared. The left-hand side would become x plus 2. The right-hand side would just become 7.39. You subtract 2 from both sides, you get 5.39. So you could use the properties of logarithms to simplify this before you did this second thing. Okay, so that's it. If you guys still need some more examples, let me know, and I can do all the even problems and post them online. So I'm going to leave that up to you. Okay, now I've finished with the preliminary stuff. We're going to just take the derivative. We're just going to do some derivative stuff, and it's just doing the chain rule mostly. And in these exponential type problems, the chain rule usually means that the exponent is u of x. Not always, but a lot of times. Unless the exponential is by itself, then you just use the chain rule normally. So, okay, so what we're going to do is we're going to say u of x is the exponent, 2x, and f of u is e to the u. So we know the derivative of e to the x, or e to the u, it is just e to the u. And then we have the derivative of the exponent, which is just 2. Not 2 dx, remember, because this is already d u dx, so it's on the left-hand side. We don't put that on the right side. It's only when we do u substitution do we have the dx, because we have du, not u prime. So that's okay. So f prime of x is f prime of u times u prime of x. F prime of u is e to the u times u prime of x, which is 2. So that becomes 2 e to the u. And then we substitute u back in, so you get 2e to the 2x. And it's kind of like, trig functions. If you have, in trig functions, if we had the cosine of 2x as being the function, then the derivative is just equal to 2, which is the derivative of what's inside, times the derivative of the cosine, which is negative the sine of, not x, but we keep the argument the same. So the same case is true here. The exponent doesn't change. That's in contrast to, say, x to the n polynomial, where the exponent changes. But here, the exponent doesn't change, but we do get this additional term in front, depending upon what the form of the exponent is. Now here, the argument doesn't change. The actual function changes. It goes from cosine to sine, or if we did it the other way, it'd be from sine to cosine. But anyway, exponential functions are pretty easy to take the derivative of, and actually that's it for that problem. So the answer is 2e to the 2x. Okay, problem 37. We get y is equal to e to the square root of x. And I'm just going to rewrite this as f of x so it fits our little chain rule situation. So the only difference is the previous problem had 2x as the exponent. This has a square root of x, so f prime of u is e to the u, and u of x, pardon me, not f prime of u, just e f of u. So then you get u of x is the exponent, which is the square root of x, which is x to the 1/2. So you take the derivative of the u of x, which is 1/2 times x to the minus 1/2. You decrease the exponent by 1. So u prime of x, we've done this many times, 1 over the 2 square root of x. F prime of u is, again, just e to the u. So f prime of x is equal to f prime of u times u prime of x. F prime of u is e to the u. U prime of x is 1 over 2 times the square root of x. And if I move this to the front and I substitute in u, I'll get 1 over 2 square root of x e to the square root of x. And that's the answer. Okay, so let me see what the problem, forgot which problem I'm doing here. 42. Okay, so 42 is y is equal to the natural log of 1 plus e to the x divided by 1 minus e to the x. So there'll be two ways of doing this. This is the u of x right here that's in the parentheses. But then you'd have to use the quotient rule. So the best thing to do here is first call y f of x. And we can use the properties of logarithms to break this up into two terms. The quotient can be broken up into two parts. And that way we don't have to use the quotient rule. It would work using the quotient rule, it's just it would take longer, more effort. Now, each one of these is going to be using the chain rule. And I'm going to just do it in one felled swoop. So what you do is you take 1 over whatever's in the natural log part. And then you multiply it by the derivative of what's here. So the derivative of 1 is 0. Derivative of e to the x is e to the x. So that's going to end up being e to the x divided by 1 plus e to the x. And then the second part is 1 over, you got a negative sign from here, 1 over 1 minus e to the x. And then you multiply it by the derivative of this term, expression in the natural log. This is the u of x part, and this is the natural log of u, basically. So you take derivative of 1, which is 0, and then you'll get negative e to the x from this negative here. So the derivative of e to the x is e to the x, so you get negative. And you could say, well, we're going to stop there, but I think we can combine these two. So you got negative times a negative, so it becomes positive. So you get positive e to the x over 1 minus e to the x. So the common denominator is going to be the product of these two. So one way of doing this with fractions is if you take these two multiplied together as your denominator. So this works when you have just two fractions. So you take these two as the denominator, and then you cross multiply. So we get e to the x times 1, this one times 1 minus e to the x, and then you have plus 1 times 1 plus e to the x times e to the x. So that's this direction. So we do this, and then we do that. Now the denominator, because you have 1, this is FOIL, you'd use FOIL here, you get 1 times 1 is 1. Then you have e to the x times 1, e to the x times minus 1, or 1 times e to the minus x, so those cancel out, and then you have e to the x times e to the x. So that will be a negative sign, so we'll have 1 minus e to the x times e to the x. Now, I'm going to simplify that in just a second. Over here we get, if we multiply it out, we get e to the x minus e to the x times e to the x plus, and then we do the second part, and you get e to the x plus e to the x times e to the x. Now, when you have a situation where you have the same base and you multiply these together, you add the exponents together. So you would get e to the x minus e to the 2x plus e to the x plus e to the 2x. And I could have just canceled them out, but I wanted to emphasize that. And the same way in the denominator, so you get 1 minus e to the 2x from this term. As you can see, you can cancel these out because you've got negative and positive of the same term. So we get 2e to the x over 1 minus e to the 2x as your final simplified answer. Okay, we're on problem 49, which is find the equation of the tangent line. So we're doing that again. Pretty much do that anytime we get a new term. So it's the same procedure, it's just a different derivative. So that's our equation, and our point is 1, 1. And if we put x equals 1 in here to the equation, you get 1 minus 1, which is 0. So e to the 0 is 1. That's where we get the y value from. Even if we hadn't, just given the x equals 1, we could calculate y. So to find the equation of the tangent line, you have to find the slope. And once you have the slope and you have this point, then you can use the point-slope formula of the linear equation. So all you do is take the derivative of this thing. Now I'm going to go, well, let me hold off on that. Let's use the chain rule. I'm not going to skip the chain rule, but I'm going to do it two ways. I'm going to just kind of show you how you do it in your head. And I'll do it the long way first, but for you guys who are more adept at this thing. So you get e to the u is f of u. U to the x is 1 minus, u of x is 1 minus x. So we take the derivative of each term, and we just get e to the u for the derivative, and the derivative of u is just negative 1. This goes to 0. The derivative of negative x is negative 1. So f prime of x is just equal to e to the u times negative 1. So that just becomes negative e to the u. From this becomes negative, and u is 1 minus x. So all you do is we just change the sign because of this negative here. Now if you were to do this kind of in your head, you'd say, okay, I know that the derivative is going to be e to the 1 minus x times the derivative of whatever the exponent is. And the derivative of that exponent is negative 1, so I know the answer is just going to be negative e to the 1 minus x. So that's how you kind of would do it. Now, so there we have the derivative. Then you evaluate the derivative at the value of x that you're interested in, which is 1 right here. So that's where I get the 1 from. It's not the y value, it's the x value. And then you plug that into your expression for the derivative, so you get negative e to the 1 minus 1. Okay, so I've substituted, that's where that comes from. It's this number right there. You get e to the 0 again, which is 1. So f prime of 1 is actually negative 1 instead of f of 1 is 1, f prime of 1 is negative 1. Okay, so that's our slope. So we can say m, which is slope, is negative 1. So then you have y minus y1 is equal to m times x minus x1 and then we just plug in the number. So y1 is 1 from there. Slope is -1. Have x minus x1, which is also 1. And then we put it in the slope-intercept form. So to do that, we have to multiply out here, so you distribute the -1 to both the x and the -1. And then we add 1 to both sides to get rid of it on the left side, so you get x plus 2. So that's the equation of the tangent line. So we're going to go ahead and plot these just to show you that it does work. So we have e to the 1 minus x. Okay. So let me bring up the graphing program here somewhere. Okay, so there we go. So the function we had was e to the, or I guess you could do exponential of 1 minus x. And the equation for the tangent line was y equals -x plus 2. So it's slope of -1, y-intercept of plus 2. And let's look at it. Okay, so there's the red curve. That's e to the 1 minus x. So it looks like an exponential function, but it's -x, so it's flipped around. Normally the exponential function goes like this and up through there, and then it's all shifted. It's a since it's part of the x term, it's an x shift, and it's shifted +1. Okay, so e to the minus x would go through here. E to the 1 minus x goes through there. And you can see right here is the tangent point. We have x equals 1, y equals 1. The equation for the tangent line is slope of -1 with a y-intercept of +2. And you can see that it is a tangent line, so that does work out.
Okay, so here's the solution to problem 62. So we have this function g of x, which is equal to the square root of x plus e to the x natural log of x. So the second derivative is, you take the derivative of the first derivative. So we're going to use just normal rules that we have. Before we do that, we have to rewrite the square root of the fractional exponent. Okay, then we'll take the derivative. This is the first derivative. So you get 1/2 x to the minus 1/2 power. So you take that, reduce the exponent by 1. Now the second is going to be the product rule. So we're going to take the derivative of the first term, and the derivative of e to the x is e to the x, times the second term, plus the derivative of, or the first term, times the derivative of the second term. The derivative of the natural log is 1 over x. So that's the first derivative. So to get the second derivative, we just take the derivative again. So when we take the derivative of this polynomial, we'll get -1/2 times +1/2, which is -1/4. Then we'll have x to the minus 3/2 power. -1/2 minus 1 is -3/2. Then we use the product rule again here, so we get actually this part. So since these are the same, when you take the derivative the second time, you'll get e to the x natural log of x plus e to the x times 1 over x. So that's the derivative of this. And then you need to take the derivative of the last term, which is also a product, but I'm going to rewrite this as x to the minus 1 power. So 1 over x is x to the minus 1 power. So now I'm going to use the product rule for this term, which is the same as that. So you get the derivative of the first term, derivative of the first term times the second, plus the first term times the derivative of the second, which is going to be -1 times x to the minus 2 power. So the derivative of x to the minus 1 is -1 x to the minus 2 power. And let's just clean it up. We have these two terms are, let's see, this one and this one are the same, because this is e to the x times 1 over x, and we have e to the x times 1 over x. So we'll be able to combine those two. So what we'll get is 1 over 4 x to the 3/2 power. So I've taken that negative exponent term, moved it to the denominator, made it positive. I've got this term here, which is e to the x natural log of x. I've got two of those, so that's going to be 2 e to the x 2e to the x, and then 1 over x. So I'm just going to put the x down there. So it's 2e to the x over x. And then the last term is going to be negative, because I got the negative in the from right here. So it's going to be negative 1, so I can drop that. E to the x in the numerator and x squared in the denominator. So that is the answer. I'm just going to check to make sure I did it right. I haven't done this one before. I don't remember doing it. And I'm going to pause it for just a second. Yeah, they did it slightly differently. What they did is when they took the derivative of this, they used the quotient rule instead of rewriting it as a product. But what you'd end up with is this term and this term combined with the common denominator of x squared. But otherwise, it's correct.
So 65 is just doing some stuff from chapter 3, but with the exponential function. So we have the function, the original function is e to the x plus e to the minus x over 2. And so they're asking for the extrema, which means that you need to look for the critical numbers, and points and inflection. So we have to take the second derivative and solve that for 0 and check that out. And then we can use the first derivative test and the second derivative test to look at the extrema, and then we can use the look at and make sure the concavity changes across the point of the possible point of inflection. So really the first step is doing the derivatives. And basically what we have is here's 1/2 times the derivative here. And the derivative of e to the x is e to the x. And the derivative of e to the minus x is minus e to the minus x. Okay, you get negative here because the derivative of negative x is negative 1. So you get that. Okay, so that's the first derivative. The second derivative is the derivative of the first derivative. So you get 1/2 derivative of e to the x is e to the x. Derivative of e to the minus x is minus e to the minus x. So you have minus times a minus, and that becomes plus, and you get e to the minus x. So that's the second derivative. So now all I have to do is set them equal to 0. So if we say f prime of x equals 0, it's equal to 1/2 e to the x minus e to the minus x. And so we don't need to worry about the half. So we just get, because that if we divide by half, this goes to 1, this goes still 0. 0 divided by half is still 0. So you get e to the x is equal to, or actually e to the x minus e to the x equals 0. Or e to the x is equal to e to the minus x. So what do we do? Well, we can take the natural log of both sides. So you get the natural log of e to the x is equal to the natural log of e to the minus x. So we get x is equal to minus x. If you subtract, add that, you get 2x is equal to 0, or x is equal to 0. So we have a critical number at x equals 0. Now the question is that an extrema? Don't worry about that. Let's go ahead and do the second part, which is you set f double prime equal to of x equal to 0. So you get 1/2 e to the x plus e to the minus x. Okay, so again, if you multiply by 2 or divide by 1/2, you'll end up getting e to the x plus e to the minus x equals 0 is where there are points of inflection. And so we get e to the x is equal to minus e to the minus x. So what does that mean? Okay, so we have to solve this for x somehow. Now we can't just take the natural log of those sides because it won't help us yet. Okay, actually this is equal to e to the x is equal to -1 over e to the x, because e to the minus x is 1 over e to the x. So now what we actually do is multiply both sides by e to the x, so we'll get e to the x times e to the x is equal to -1. And so what do we get? We get e to the 2x is equal to -1. Now the problem is, if you take the natural log of both sides now, you get the natural log of e to the 2x is equal to the natural log of -1, but that does not exist. So that would indicate that there are no values of x where the second derivative equals 0, which would indicate, so you get 2x is equal to does not exist, which would mean there are no values of x where this has a second derivative of 0. So let's see if that's true or not. We'll keep going, assuming. So there's no points of inflection. Which kind of bothers me, but should I let it bother me? I don't know. Okay, well, if it does, I'll just forget about the recording. If it works out, we'll be good. Okay, so now all we have to do is figure out, does the function change from increasing to decreasing across the critical number. So we're going to use the first derivative test. Another way of looking at it is you could use the second derivative test and say, is at x equals 0, is this positive or negative? Well, you get e to the 0, which is 1, plus e to the minus 0, which is also 1. So you get a positive result, which would be concave up, which would be a minimum. That's true. Okay, so let's see if that works out. So here's our interval from -infinity to 0 and from 0 to positive infinity. And then we have our test point. So this is interval. So we could take -1 and +1. F prime of the test point. So remember, f prime of x is equal to 1/2 e to the x minus e to the minus x. And the half really doesn't factor into the sign of it. So what we'll end up with is, let's just check out the sign of this. So you get e to the -1 minus e to the negative of -1. Negative and then -1. So e to the -1 is 1 over e. And then you subtract off basically e. Well, 1 over e is 1 divided by 2 something, and this is -2 something, so you end up with a negative result. So the answer is negative. And if you do the same thing here, you'll get positive. So what does it say? What are the comments? Since the first derivative is, if the derivative is negative, we're decreasing. And here we're increasing. And so we go from decreasing to increasing, and therefore it's a minimum. which is what I said it was from here, actually up here, because I said this was positive, second derivative was positive, which means it was concave up, which also means a minimum. So both of those would indicate we have a minimum but no points of inflection. So let's go to the graphing program. And the function is, it's exponential of x plus the exponential of negative x divided by 2. And we graph that. So there it is. That's what it looks like. And so you can see that we have a minimum at x equals 1. To the left, we are decreasing. To the right, we're increasing. We have concave up. So this all agrees with what we said, that we have an extrema at x equals 0, and we have no points of inflection because it is always pointing concave up. So we're right. I was thinking of another function that I had in my mind, but it wasn't correct. Okay, so there we go. So what is the extrema? Well, the maximum is infinity. The minimum is going to be f of 0. And f of 0 is e to the 0 plus e to the minus 0 divided by 2. And so we get e to the 0 is 1, e to the minus 0 is 1. And so we get x equals 1. And let's go back. I'm just going to look at the graphing program. And that's right. Okay, so the minimum y value was 1. So everything works out perfectly. Okay, so we're doing problem 86. So these are the integration parts of the e to the x examples. So basically, it's just u substitution. We just have a new function that we have to deal with. So anyway, this is problem 86. So remember what we do is we pick u. So u is equal to, well, typically if the exponent is something other than just x, then, or negative x, then that is u. And then you calculate du. So we get 4x, actually it's negative 4x squared. So the derivative is negative 4x cubed dx. So that derivative of negative x to the fourth is negative 4x cubed dx. And then we look at the original equation, see what we've got besides our u function. And you get negative 4x cubed dx. So that is du exactly, so we don't have to really change anything. The third step is to substitute back into the original equation. So we get e to the u times du. Okay, so now we know the integral of e to the du is just e to the u. So the answer is e to the u, the integral is e to the u plus our arbitrary constant. And then step 5 is to plug u back in. So we get the answer is e to the negative x to the fourth power plus c. So that's the indefinite integral, has an arbitrary constant c as part of the answer. Okay, number 88. So let's look at this. The integral of e to the 1 over x squared divided by x cubed dx. Just like in the previous problem, if you have an exponent that is other than just x or negative x, then the exponent is typically what we decide is u. So it's going to be 1 over x squared, which is the same as x to the minus 2 power. So when we calculate du, what we'll get is negative 2, which is the exponent, times x to the minus 3 power, because we're taking the derivative here. So we get negative 2 e to the x to the minus 3 dx, which, if we rewrite that, it'll be negative 2 divided by x cubed dx. So let's see what we have here. We have dx divided by x cubed. So let's solve for that. So dx divided by x cubed is just equal to du divided by negative 2. So for dx over x cubed, we're going to substitute du minus 2. So that's the substitution we make. So our original integral becomes e to the u, where u is 1 over x squared, times du divided by negative 2. And we can factor out the negative 2, which is in the denominator, so you get negative 1/2 the integral of e to the u du. So now we're where we need to be. We know the integral of e to the u du is just e to the u. So the integral is negative 1/2 e to the u plus c. So that's the integration part. Actually, yeah. So step 4 was to integrate. Step 3 was to substitute. Step 5 is to substitute u back in. So you get negative 1/2 e to the u, which is u is 1 over x squared plus c. So that's the integral, the result. Okay, problem number 91. Here we have the integral of e to the x times the square root of 1 minus e to the x dx. So in this case, this is a case where it's not the exponent, because notice it's e to the x. So we're not going to choose u as x, because that really doesn't do anything good. I'll just change the variable. It doesn't do it. Save it. So the next thing, the other option is if this exponent is not something that's an equation, just x, then we go back to kind of a previous rules, which says that we take stuff that's the argument of a function or something that's in a parentheses. So if I rewrite that, you can either say it's the argument of the square root, or you can rewrite it as a fractional exponent. So in this case, u is equal to 1 minus e to the x, term in parentheses. So you calculate du, which is going to be negative, the derivative of 1 is 0. You have negative times the derivative of e to the x, but the derivative of e to the x is just e to the x. So du is negative e to the x dx. So we go back to the original equation. What do we have when we take out that part, which is the u to the 1/2 power, is we get e to the x dx. So that's what we want to solve for. We want to solve for e to the x dx. So we just multiply both sides by negative 1. So e to the x dx is negative du. Okay, now we can make the substitution. So the original integral becomes, well, e to the x dx is equal to negative du. So let's put that out there, negative du. And this expression in parentheses just becomes e to the, and pardon me, not e, but u to the 1/2 power. So even though the original expression has e to the x in it, the integration is really an integration as a polynomial, as a power. So let's factor out the negative sign from here to there. So you get u to the 1/2 du, which is the integral is going to be equal to u to the 3/2 divided by 3/2 plus our arbitrary constant c. And then we, instead of dividing by 3/2, we multiply by 2/3. So we get 2u to the 3/2 divided by 3. 2u to the 3/2 divided by 3 plus c, and then we can substitute u back in. So the answer is 2/3 times the quantity 1 minus e to the x to the 3/2 power plus C. And that's our answer. You kind of check if you want to, if you took the derivative of this, the constant would go to 0 because the derivative of the constant is 0. You'd have 3/2 times 2/3, which would be 1. And then when you took the derivative here using the chain rule, you get negative. You take the derivative here and you get negative e to the x. So the negative times the negative would end up being positive. And that's where you would end up back to where you started. Okay, so we're going to skip a couple here, go to number 98. So we have the integral of the natural log of e to the 2x minus 1 dx. So you may be tempted to make this u. The problem there is that this is not, you get the natural log of u, but if you take du, you're going to end up with, well, I guess you could do it. Anyway, that's the hard way of doing it. Hopefully, you recognize that we have the natural log of e to something. So we can actually use the properties of inverse functions to say that this is equivalent to just 2x minus 1 dx. So we don't have to do anything super difficult because that's the answer. So now you integrate that, and so you get 2 times x squared over 2 minus x plus the arbitrary constant c. So this is the integral of that is that, integral of that is that, and then you add your arbitrary constant c, so you get x squared minus x plus c, and that is your answer. Okay, so we're going to get some practice here doing definite integrals, and then we can do the same thing that we did in previous cases, is that we can just redefine the limits in terms of what we define as u. So we look at the exponential function, we see that the limit, the exponent is something other than x, so that means that u is going to be equal to the exponent. And then we calculate du, which is going to be negative 2, derivative of x is 1, so we get 1 times negative 2 times dx. We look back at the original equation, see that we only have dx, so we solve for dx. That's going to be equal to du divided by negative 2. Let's go ahead and redefine the limits. So when x equals 0, u equals negative 2 times 0, which is 0. And when x is equal to 1, u is equal to negative 2 times 1, which is negative 2. So with the substitutions of the limits, so we integrate from we actually integrate from 0 to negative 2, which is still fine, so we keep it all straight. Instead of from 0 to 1, we go from 0 to negative 2. Then we have e to the u, and du is equal to, or dx is equal to du divided by negative 2. So we'll factor out the negative 2, which is in the denominator, so it comes out as a fraction. And then we have the integral from 0 to negative 2 of e to the u du. Okay, so this is the formula that we're looking for. So the integral is negative 1/2 e to the u, and we evaluate that from u equals 0 to u equals negative 2. So we have that straight line, and we have you don't really need to put the u's in there. I'm just doing that to emphasize that we changed the variables. Okay, now we plug the numbers in. So you get negative 1/2 times e to the minus 2 minus e to the 0. And e to the minus 2 is the same as 1 over e squared, so this is really equal to 1/2 times 1 over e squared minus e to the 0, which is 1. Then let's just add one more page here. So what we get is negative 0.5. Negative 0.5, which is negative a half, times 1 divided by e squared minus 1. And the final answer is, actually I just put it here, 0.432. So this is a definite integral, so we get a number. And that would be the area underneath this curve, the original curve. And let's just go ahead and look at it. So it's about a half. So we should be able to at least estimate, see whether it's correct or not. So we go to the graphing program, and the function that we're looking at is e to the minus 2x, exponential minus 2x, and I'm going to graph it, and I'm going to click standards to get it in there. So what we're doing is we're integrating from 0 to 1. So it's this area right under here. So let me just highlight that. So it's this area. So from x equals 0 to x equals 1. And we're saying that area is about a half. So does that make sense? A little less than a half. Well, you know, this is 1 by 1. So this whole thing is 1. If we drew a diagonal here, then each one would be a half. So this would be a half and this would be a half. And so this is less than a half by this much. So it should be 0.4 something, around 0.4, based on our estimation. So let's go back and see what we got from the number. So our answer was 0.432, right there. So that makes sense. Okay, problem 101. We have the integral from 0 to 1 of x e to the minus x squared dx. So first thing we do is identify u. This is not just x, so that's probably going to be u. Take the derivative. So we get negative 2x dx. Negative from here, 2 from the exponent, reduce the exponent by 1, we get x and add dx on the end. We look back at the original equation and see what we have. Well, we have x dx, so let's solve for that. X dx is equal to du divided by negative 2. Since we're doing a definite integral, we're going to redefine the limits. So when x equals 0, u is equal to negative 0 squared, which is 0. When x is equal to 1, u is equal to negative 1 squared. Not negative, the quantity negative 1 squared, but 1 squared and negative, so it becomes negative 1. Okay, that's step 2. Step 3 is substitution, so we substitute in both our limits. Our limits go from 0 to negative 1 now. And instead of from 0 to positive 1, our original equation becomes e to the u times du divided by negative 2. We factor out the negative 2, and that gives us the integral of u du, which we know the answer, that's e to the u. So the final answer, the result of the integration, which is step 4, is to integrate. You get negative 1/2 e to the u, and we're evaluating between u equals 0 and u equals negative 1. So our final step is just to plug in the limits. So we have our negative 1/2 times e to the minus 1 minus e to the 0. And notice I don't have to square anything because I've already squared things when I redefine my limits. And that's the same as negative 1/2 e 1 over e minus 1. E to the 0 is 1. And this is 1 divided by 2.78. So this is going to be a negative quantity in the parentheses. And then we'll multiply it by a negative number, and we'll end up getting a positive number, which gives us a positive area. So let's try this. So we have 1 divided by E. E, where is it here? E to the first power. Or to, yeah, E to the first power. Or E dividing by 1 over E. Minus 1, it's a negative number, times negative 0.5 gives me negative 0, or actually positive, because I've got positive times of negative. Gives me the definite integral is 0.316. So that's the value. And again, I'm going to plot this. So let me share that with you. So the function is equal to, in this case, x times e to the negative x squared. And we're going to go between 0 and 1. Let's be x limits. And we'll graph that. Graph. So there it is. Let me zoom in a little bit and be wide. Wrong direction. 0. Okay, so anyway, that's the function. And it's saying this area is 1/3. And you can kind of see here's 1/3. So if I drew a horizontal line across there, I would end up with, some of it being above the curve and some being below the curve, which has to happen for an average. Let me see if I can just draw this across here. So it's like somewhere here. So that would this thing, well, if I could draw it right, this little area here should have about the same areas that's into there. And so what you have is this, we're over predicting it here if we took that as the average value, and we're under predicting it there, and this green area should be equal to the blue area. And to get this rectangle, so this is your average value as well. This little blue dashed line will be the average value for this period of time. So it looks good to me. Okay, let's do another one here. Another definite integral. So we have the integral from 0 to the square root of 2 of x e to the minus x squared over 2 dx. And in some ways it's very similar to what we just did. The only difference is the exponent is slightly different, but in all intents and purposes it's the same basic idea. So u is going to be the exponent. And then if you take du, you would get negative, derivative of x squared is 2x. And so we get negative here, 2x, and then we divide by 2, and you see the 2's cancel out. So we get du is equal to negative dx, or dx is equal to negative du. So we can make that substitution. Oh, forgot the x part here. Okay, so let's do that. So that's negative x dx. So x dx is negative du. So if we multiply by negative 1, we'll get x dx. Okay, then we redefine the limits. So when x equals 0, u equals negative 0 squared divided by 2, which is 0. When x is equal to the square root of 2, u is equal to negative the square root, quantity square root of 2 squared divided by 2. And that's equal to negative 2 divided by 2, which is equal to negative 1. So that's my new limit. It's negative 1. So I can make substitutions into the original equation now. So the integral becomes the original integral. Now it becomes the integral from 0 to -1. That's the u limits. We get e to the u times, okay, x dx is negative du. So we factor out the negative sign, and we integrate from 0 to -1, e to the u du. The integral of e to the u is e to the u, so we get negative e to the u evaluated between 0 and -1. Again, we don't have the arbitrary constant because that cancels out when we do this subtraction process. So we get negative quantity e to the -1 minus e to the 0. E to the 0 is 1. So we get negative 1 over e minus 1, or 1 minus 1 over e, which is going to be equal to 0.6 or 0.7 something, because we have 1 minus 1 divided by e, and that's 0.632. So that's the answer. That's the area underneath the curve. Okay, the last problem is one of 7, which is a differential equation. And so what do we do with differential equations? Well, what we do, and we have a constant here, e to the ax squared. So this is a constant. We'll just leave it as a constant. So when we have differential equations, we multiply both sides by dx. So you get x e to the ax squared. Now, since we're not given an initial condition, all we can do is get a general solution, which means we're going to have an arbitrary constant. So we integrate both sides. Like that. So the right-hand side just becomes the function y of x, or f of x, or y, whatever you want to call it. And on the right-hand side, we have to use the chain rule. So let's move this down. Not the chain rule, but u substitution. So u is going to be equal to ax squared. So du is equal to 2ax dx. So the 2 comes from the exponent. We keep the a, it's just a constant. Reduce the exponent by 1 multiplied by dx. Okay, so what we get is we get the integral. Before we do that, though, we have x dx. So we need to solve for x dx. X dx is equal to du divided by 2a. So I divide both sides by 2a to get that by itself. So we go back here, and we have e to the u times du divided by 2a. So x dx becomes this. Factor out the 2a, so we get 1 over 2a, the integral of e to the u du. Okay, so now we're in good shape. We integrate, so we get y of x is equal to e to the u divided by 2a plus our arbitrary constant, which means that we have a general solution. And then we substitute u back in just like we normally do, and we get e to the ax squared divided by 2a plus c. So that's our solution to the differential equation. We're given information about the derivative as a function of x, and then we're able to solve for actually what is the function, not the derivative of the function. And we would have a complete, we'd have to be given 2 pieces of information, one to solve for c and one to solve for a. So, you might have an initial condition to solve for c and some point in time to solve for a.